So last week we defined what a contractual relation is between clients and supplier, and we spoke about the ideas of modularity and also abstract data types. So now this week we'll start talking about the different, more like a list of abstract data types week by week. And this week we are definitely going to talk about the basic ones, namely stack and also queue. And even though they are simple and basic, we can already see interesting applications already using these two data structures and also abstract data type. Let me just use one single slide just to recap and also to kind of connect from what we learned from last week, and then we'll move on to our first ADT for this course, which is stack. And we want to really build ADTs for reusability, right? You want to build different modules so that you can really assemble them into useful pieces or useful bigger system. And ADTs are simply reusable software components that are common for solving many real-world problems. You can think about each ADT that we're going to learn in the course is going to be some common ones that people usually use for solving their problem. And whenever you're building your own application beyond this course, you can either number one, reuse the ADT that you learned about, or number two, you can actually build your own ADT by reusing the common ADTs or common data structures. That will be the roadmap to really go beyond this course. And so what we're going to learn in this course as the standard ADTs will be stacks and queues. We're going to cover them this week, and also we're going to talk about trees and graphs, and we're definitely going to talk about tables. But for lists over here, it's actually rather simple ADT. We might be able to get there if time permitted. Otherwise, it should be very easy for you to study on your own beyond this course. But we'll definitely cover the more challenging ones to make sure you're okay. And an ADT, once thoroughly tested, can be reused by. So you want to make sure whenever you build ADT, you can think about ADT can be a single Java class, or it can be simply the assembly of several Java classes. It depends how simple it is. And once it is thoroughly tested to make sure it is correct, it can be reused by. Either it can be simply used by clients who just want to use ADT for their application. Or, more importantly for you as a supplier, you may actually want to use other ADTs while you're building some new ADTs, which doesn't really exist ever. In which case, you may decide, in order to build my own ADT, I want to make use of a stack. For example, let's say you want to build a calculator ADT for postfix numerical expressions, which is something we'll talk about when we talk about the application for the Stack ADT. Let's say you're building such calculator ADT, in which case you can definitely make use of other ADT, for example, stack, right? So I would say the second point is actually even more relevant to your endeavors, because you definitely have to build ADTs very often, and sometimes you just want to make use of other ADTs. And as a supplier, you're obliged to implement standard ADT. You should really know how to do them. So I would say try not to rely too much on Java library classes at this point. You really want to know how to build each one of the standard or basic ADTs that we're going to talk about throughout the course from scratch on your own. You want to know how to build the basics. So later on, when you actually get to build something completely something completely novel and something completely new that no one actually has built before, in which case your creativity can really be supported by how solid you are on building the basic ADT, right? That's something I will advise right in the beginning. And you can think about implementing standard ADTs like Lego building blocks, right? So remember the first example we did for modularity. You want to know how to really build the building blocks well yourself. And then later on, you can actually design algorithms using the standard ADTs. And of course, you can see the analogy over here. Either we talk about the building bricks, or we talk about the masterpieces, the assembly of the basic pieces. And for basic data structures, we have already covered each one of them in detail. You can either use an array, use a singly linked list, or doubly linked list. And you already know their performances in terms of the running time very well. Right, for each standard ADT, you should know its interface. So whenever you're learning a new ADT or you're defining your own ADT, you want to make sure the interface is rather clear. What does it contain in the interface? Number one, the data that's actually stored in the ADT, and also the each operation manipulating the stored data. If you want to implement this in Java, for example, in that case, you want to make sure at least this part over here is very clear. If you actually want to use the Java interface notation, that's something we'll see for both Stack and Queue this week. And so whenever you are building your interface for the operation, it should be made very clear about two things over here. Number one, how are the clients of your ADT supposed to use the method, right? How are they supposed to use it? And they really should know how they are supposed to follow the instruction. Remember the microwave example we did, right? In order for the obligation for the clients would be the preconditions. They have to make sure any input constraint, for example, a method has the caller or the clients must satisfy them before they make the call. And number two, assuming that the preconditions are satisfied by the clients, what will be the obligation on the other side for the supplier? It would be, well, they want to make sure the post conditions are satisfied, meaning that given that the instructions have been followed, the service must be guaranteed upon the termination of the operation or the method, right? That's something we spoke about last week when we tried to define the contractual relationship between the supplier and also the client, right? And also you want to make sure it's either made clear or made at least to the supplier about the time and also the time complexity, right? It should also be very clear to the potential user about how efficient the method is, right? That was a very quick walkthrough about what we actually covered last week, and also just try to connect to what we are going to talk about right now. And the first ADT that we will introduce to you will be something called Stack. It's a very basic and also simple data structure. However, it's incredibly useful in practice. We'll see. I'll give you different use cases in a moment. Well, let's define what a stack is. A stack is simply a collection of objects. Well, just a collection. What's so special about this collection? Objects in a stack are inserted and removed according to the so-called last in, first out, or LIFO principle. Right? So this principle over here, maybe just from its literal meaning, you can already imagine exactly what it means. That means whatever object that was the last one going into the collection, whenever we want to retrieve something out of the collection, they should be the first one to come out, basically. But we'll see exactly how that works. And so here are two important points about the LIFO property. Stack, unlike an array, you just cannot really access any arbitrary elements in the stack, but you can do that for the array, of course, or linked list. So for the stack, you cannot access any arbitrary elements of a stack. You cannot say, I want to go to the second elements of the stack. I want to go to the last element of the stack. No, you cannot do that. There's only one element, only one special item called the top that you can actually access. So you can only access or remove the most recently added element. So this is something called the top, which I will go over with you in a moment. Right. So these are the two very important principles you want to remember for the last in, first out property for the stack. Right. And some real life example. If you ever go to a restaurant for buffet, right, like the all you can eat lunch or dinner, in which case the way they serve the plates, right, they kind of put the plates on the table, and then you can see the place on the top is really the last plate they actually put on the pile, right? That's guaranteed. So that's kind of the last in, first out. Let's say I want to take a plate from the pile over here. In that case, the plate on the top, which I take out, should be the last one that was inserted into the pile. That's number one. And number two, not too sure how many of you actually has this kind of nice memory, but these are kind of like a candies. You can actually, not too sure if maybe you can still buy them nowadays. But if you buy them, so you're going to load different candies into this nice little stand over here for the toy, and then the first candy you took out should be the last one you put into the stand, right? So these are just two, like a real life example about stack. You can definitely see stack examples everywhere, but so these are just two examples just to give you some intuition. Right, let me go over some informal interface about the stack operations. I'll talk about their precondition and postcondition for each one of them, and then I'll do some visualization about a stack. And then we're going to go on to implement stack in Java. Right? What about the stack ADT? Exactly how do we define its interface? Let me talk about the different operations. So there is one operation called the top. It's the only special element you can access in the stack. What will be the precondition? In order for you to really retrieve the top, or to know what the top is for the stack, the precondition is, of course, the stack cannot be empty. If the stack is empty, and calling the top is gonna trigger maybe some exception. Right? You can think about whenever there's any precondition violation, there should be some corresponding exception thrown from the class or the objects. What about the post condition? Given that I'm trying to inquire about the top of the stack when the stack is not empty, meaning that I satisfy the precondition, what should be the corresponding post condition? Well, in that case, of course, I should be returned the top. So that means I should be returned in the post condition, return the item that was last pushed onto the stack. So the verb push over here is a very special terminology just for stack, where you don't really say you want to insert into the stack, because you don't really insert into some arbitrary position in the stack. You only try to push onto the top of the stack. Just notice the verb I'm using over here. Right, so that's about the precondition and postcondition. So I want you to really get used to this pattern over here. Whenever you want to describe the operation of some ADT, and you want to know what's really the corresponding precondition and what's really the corresponding postcondition, right? Okay, second operation. What about the size? I want to inquire about the size of the stack. How many elements have I pushed onto the stack so far? What will be the precondition? Is there any circumstances under which I really just cannot inquire about the size of the stack? Well, what if the stack is empty? In that case, should I be forbidden to inquire the size of an empty stack? The answer is no. In that case, the size is simply just 0. So it turns out, in this case, the precondition is simply none, meaning that this calling this operation is unconditional. You can always call that without ever worrying about to trigger some exception, right? Notice that, right? So precondition may be none, but for postcondition, it should never be none, because it should always be well defined about what exactly the operation would do for the ADT. So what will be the postcondition for the size? Well, it should really return some number that would denote the number of items pushed onto the stack so far. Next one is empty. So this is more like a Boolean operation. Well, I want to inquire whether or not the stack is empty. It's kind of like a special case about the size. If the size happen to be 0, in that case, its empty should be true. Otherwise, it should be false, right? So the precondition will similarly to the size operation, none. You can always inquire about if the stack is empty. What about postcondition? Well, it's going to be more like a Boolean value. So you want to know whether or not there is no item in the stack. If there's no item in the stack, in that case, its empty is going to be true. If there's at least one item in the stack, in that case, its empty is going to be false, right? Very straightforward. And what about the push? So we don't really say you want to insert an item or add an item into the stack. That's not how we normally do it. We have some special terminology for insertion and deletion for stack and also for queue. That's something we'll see. But for stack, you want to remember a special term we'll call push. Okay, I want to push the item, the input item over here. The type over here is not that important. It will be generic anyway when we implement it. But what will be the precondition? Precondition will be, well, if I just keep pushing items onto the stack, the pile is going to grow higher and higher. There's got to be some limits realistically, because the memory for your computer after all should be bounded. So the precondition should be the stack is simply not full. And it will not be full with respect to some certain maximum capacity. That's something you will see when we see the actual implementation. What about the postcondition? The postcondition will be, well, if you want to push some item onto the stack, that means this item over here is going to become the new top of the stack, because the top is simply on the top of the pile. If you try to stack another thing onto, push another thing onto it, so the new top is going to be this new item over here. Right, so that will be the postcondition. Really try to get used to the idea about precondition, mainly constraining about your inputs, and also the postcondition, which would be what kind of output would you get as a service. The final one is called the pop. Right, we say push for insertion and pop for deletion. Okay, in order to, what about the pop? Is there any precondition for the pop? If I pop simply means I want to remove the current top. Right, that's the most intuitive way to think of it. Well, in that case, if the stack is simply empty, there's no way for you to remove the current top because there's no top. So similar to the case where there is a precondition for the top where the stack is simply not empty, right? So the pop should have the same precondition, meaning that the stack is not empty. If the stack is empty, you just cannot pop it off. What about a post condition? Well, the post condition should really somehow remove the top, and also in Java convention, we also return the top of the stack. That's something you will see, right? It's not really a pure mutator that you normally see. You will see exactly what I mean when I show you the code. Right? It's a very quick walkthrough about the ADT for stack. It's a very simple interface to really understand, even informally. Okay, and I would like to just give you some very quick visual illustration about how exactly stack will work, and also I will suggest how you would actually trace the stack whenever you have whenever you need to use a stack ADT in your own algorithm. Right? Let me talk about it. Right? I simply got different operations over here. I simply say initialize a new stack and also push 3 items into it. And also we're going to pop different items into it. We want to see the order. We want to see exactly how the last in, first out, or LIFO property can be exhibited. Let's take a look. The way we usually trace a stack is by drawing something like this. You may have already seen your either myself or your earlier instructor drawing something like this, where when they try to simulate a call stack in your recursive call. So that's exactly the same idea. Okay. And by the way, so when we actually talk about the call stack, when we taught you recursion in the earlier OOP course, stack over there is exactly the stack over here, last in, first out, right? All right, let's take a look. So if you try to initialize a new stack, that means it's simply just empty. No elements have been pushed so far. It's empty, should just be true. And also, what will be the size? It will be 0, and the top is undefined. So I would say not applicable. If you try to call the top on a new stack, you should really get some corresponding exception for the precondition violation. All right, let's now do this next one. The next one, we're gonna push 5 onto the stack. So we simply push 5 over here. After this, its empty will just be false. The size will be incremented from 0 to 1, and the top has now become 5. Right? Very straightforward. And let's try to push another one. And push another 3, you will just stack it on top, on the pile. Right? So here, its empty is still false. And also the size incremented from 1 to 2. What about the top? The top is right now, rather than 5, is going to be 3. So every time you push something onto the stack, if allowed, the new top should really become that input elements. So in this case, it will be 3, right? You can see that the correspondence. 3 correspond to 3 over here, and the 5, the new top, correspond to the 5 over here. Okay, one more. And we're gonna push 1 over here, and remains to be not empty, and also size will be 3, and also the top should now become 1, right? Because I stack on top 1. The top rather than here is going to be over here, the top. Right, so far we have only pushed items into the stack. So which one was the last one that went into the stack? You can see here, this was the last item. Last item pushed in the stack. So that's kind of the last in part for the definition, right? The last in, right? And we want to see the first out part, the second part for the LIFO property. Let's now take a look. Well, let's say I'm now trying to pop, right? Notice that the pop over here doesn't take any input parameter, any arguments, just pop. In that case, we're going to remove the current top over here, right? I'm going to remove this one here, and then it's going to be gone. And it will be returned to whoever the caller is, just for their further manipulation. Right? So after I pop it, it still remain to be true. It still remain to be not empty. So its empty should be false. Remain to be false. Size should be decremented from 3 to 2. And what about the top? Top, you can see now is being changed to 3. Okay. And one thing that's also very important to remember for the pop operation, which is not only that it is going to remove the current top, which is 1, but also it is going to return that old top, because now the new top will be 3 over here. But the old top is going to be returned back to whoever the caller is, so they can actually do manipulate it further. right? Let me write it down. Over here, the pop is actually going to return the 1 over here. And the 1 is corresponding to the old top. The new top is actually 3 over here. And let me just write one more thing over here. You can think about the 1 over here that's being popped was the last inserted or last pushed elements. And it is this particular element that was actually removed from the first pop operation. And what about the new top over here? The 3 over here. The 3 over here is the second last pushed elements. Right? You really want to make sure you understand the reverse order that I'm suggesting over here. Right? Let's move on. And let's say we want to do the second pop over here. Right? We're going to pop the current top, which is 3. So we're gonna pop it off. We're gonna remove it and also return it back to whoever the caller is. So we're also going to return at the same time, return the old top, which is 3. After this, what should be the status for the stack? Remains to be non-empty, so it should be false. Size should be decremented from 2 to 1, and also the new top would be the third last push elements. In that case, it would be 5. Over here, right? So far, so good. Let's do the last pop. The last pop is going to be actually remove the current top, which is 5. So we're going to remove the current top, which is 5. We're going to remove it, and then going to return it as well. So that means the pop is going to return the value 5. And what will be the status for the stack right now? Because we have removed the third last pushed elements of a stack that's actually of size initially of size 3. So in that case, the stack will become empty. So it's going to be true over here, and then the size will become 0. And now for empty stack, you cannot actually invoke pop anymore. So that will be non-applicable. Otherwise, you're going to get precondition violation. Right, pretty simple operations with the push and pop together. But the most important thing, as I will annotate right now, is the last in, first out property. Let's see. So to really observe the last in, first out property, you want to look at a series of push and pop operation. So you can see the push, we push in this order, 5, followed by 3, followed by 1. But when we try to pop, we are not going to get 5 followed by 3 followed by 1. We're going to get exactly the reverse order. That means we're going to get 1 followed by 3 followed by 5. Right? So the exact opposite. So that'll be the final remark I would like to write down. And then we're done. Okay? For the basic introduction to stack. So let's now look at the order in which elements are being popped from the stack. Okay, let me do better. The order in which items or elements are pop off the stack is the reverse of how these items were pushed onto the stack. Were pushed, right? So this is exactly the last in, first out property that we want you to learn. Last in, first out. And don't really underestimate about the last in, first out property. It's actually incredibly useful for many practical applications, as we'll see later. Right, let me highlight. So here, the popping off property is exactly the reverse of the pushed order. Alrighty, let's now move back to the slides, and you can definitely still go over this table of the illustration, which is basically identical to what I did on the iPad. But if you follow through my visual illustration, that should be enough. And let's now talk about how we can implement a stack as a Java interface.